All right, we are still in 2.2 and we are still talking about polynomial functions. So today we're going to talk about some new notation. I may have used some of these words in class before, but I'm going to say it officially this time. So finding zeros of a polynomial, basically solutions to the equation f of x equals 0, that's what we call a zero, is one of the most important problems in algebra. There's strong interplay of graphical and analytical approaches, meaning sometimes zeros help us graph the function, and sometimes the graph helps us find the zeros. So they're usually places where we're looking that are important to us because there usually ends up being our solutions to our polynomial functions. So we say, so these are all equivalent statements. If f is a polynomial function and f of a, so this is like some value a here where a is just a number, is 0, then we say that x equals a is a 0 of f. Okay, so it's a way that it's just a thing that we say. Basically it also means that it's an x-intercept down here, that the point a0 is an x-intercept. So we often refer to these interchangeably as an x-intercept or the 0, right? That's just what we call it. It's when it's this is the value I plug in for x that'll give me 0 as my y-coordinate, so we call it the 0. It also means that x equals a is a solution to f of x equals 0. And also if we work backwards, it means that x minus a is a factor of f, right? So when we're factoring quadratics, right, basically we get something that looks like x minus 2 times x plus 3, and we have it's equal to 0. Well, solutions, right, these would be x equals 2 and x equals negative 3. These both give me 0 when I plug them in. So these would, I would say that x equals 2 and x equals negative 3 are zeros of my polynomial. Okay, I can also see that basically when I get x equals 2, then one of the factors was x minus 2. And when I get x equals negative 3, then the factor that goes with it is the x plus 3. Okay, so I may have said 0 in class. I've been trying to be pretty consistent with my f of x equals 0, but this is, we also call them zeros, especially the book often calls them zeros. So f of x equals 0, these are all equivalent statements. All right, so once we know that we have some zeros, let's look at this other. So there's one more thing I want to talk about in this lecture, and these are repeated zeros. So maybe you noticed, and you can go on Desmos and play with some of these, but sometimes we get, when we go to factor things, we get repeated zeros. They means the same factor shows up more than once. So maybe something that looks like this, where I get f of x equals x minus 4 cubed times x minus 2. So the x minus 4 here with the 3, it's a repeated 0. Now technically I could write it out 3 times like this is what it literally means. But when we're solving polynomial functions, we always set them equal to 0 because, I mean, we factor them and set them equal to 0, so there's no point in me unfactoring this. So this particular factor is considered a repeated 0. Now, interesting things happen when I get repeated zeros, okay? So when this value of k, now when k is 1, you may have noticed when I go to graph a quadratic function, like if I had x plus 2 times x minus 1 is f of x, then when I go to graph these, like solutions to f of x equals 0, you can see that f of negative 2 would be 0, and f of 1 would be 0, right? They're just solutions. I set x minus 1 equals 0, and I get 1. Here I get x plus 2 equals 0, and I get negative 2. So I'm writing it like this. When I go to graph these are x-intercepts. So I have a place here and a place here. And basically my function looks like this because I know it has a leading coefficient that's positive, even though it's not explicitly stated. It's implied that it's 1 because there's nothing else there. So these values, they cut through the x-axis. They're x-intercepts. And when I go to draw my graph, they actually cross over here. Okay? Now when I get a repeated 0, that doesn't always happen. Now so let's look at if I have x minus a to the k, and k is even, then what ends up happening at x equals a is I get what I consider, what I call a bounce. It's bouncing behavior. So for instance, if I stick with my quadratics here, if I were to graph f of x equals x minus 3 quantity squared, here I have a repeated 0 where my k is even, what I find here at x minus is that I end up with this graph, right? We know how to work with this. This is x squared shifted right 3 units. And so it's sitting there, right? So at x equals 3, even though it's an x-intercept there, it's not actually crossing over the x-axis. It just bumps it. So my graph, it just bounces off the x-axis here, right? So it doesn't actually cross over. So that's what happens when this power, this repeated 0, is even. So that's if it's a 4 or if it's a 6. Now, we also we've had things that have looked like this as well. So if I use x minus 3 quantity cubed, right, this is the graph of y equals x cubed shifted right 3 units. And so x cubed, right, it looks like this. And so this time I have a repeated 0 here with a 3. And so that's an indication that I get a cross, okay? So when my repeated zeros show up and they're odd, then I'm going to cross over the x-axis. When they're even, we get this bouncing behavior. We call this, we talk about this as multiplicity. Basically, it's the number of times that this is multiplied together. So when the multiplicity of this factor is even, that's what we say, meaning it's 2, so it's even. The multiplicity of the factor x minus 2 is even. We get a bounce behavior. And when the multiplicity, the number of times this factor shows up, is odd, we get this cut-through behavior. So let me write this down. We say multiplicity. So when k is odd, we get a cut-through. We cross over, and when k is even, we get, and k being the exponent here, we get this bouncing behavior.